Good morning, everyone. I am Harshanjan.
I am Ayush Tejashvi.
I am Yes Kumar Senma.
We are the students of Indian Institute of Engineering, Science and Technology, Shibpur. Today, we are excited to present our embedded system project titled Washing Machine Simulator using PIC16 F877A microcontroller. This work was carried out as part of our internship at Emertxe Information Technologies, focusing on real-time embedded application. The goal of our project is to design and simulate a miniature version of a fully automatic washing machine. We have used the PIC16 F877A microcontroller to manage core functionalities such as washing, rinsing, spinning, and user interaction, thus demonstrating the principle of embedded control system. Here is the roadmap of our presentation. Introduction, we will understand the problem statement and our objective. After that, we will look into the embedded system overview, key characteristics and classification. After that, component used, like breakdown into hardware and software, pick microcontroller, its architecture and relevance to our design, programming language, why embedded C was used and its advantage. And after that, we will look into the peripheral devices like LEDs, LCDs, interrupts, and timers used in this project. After that, we will look into demo and the conclusion, a walkthrough of our simulator in action, and the final thoughts. We hope this will give you a well-rounded understanding of how embedded systems are used to control real-life application. Washing machines are vital in today's fast-paced lifestyle, reducing the need for manual labor in household chores. There are generally three types. Manual machine requires complete human intervention. Semi-automatic machines use some assistance. Fully automatic machines, which are increasingly popular, require minimal input after loading. Our goal was to simulate the core function of a fully automatic machine in a cost-effective, modular, and programmable setup. We implement timer control washing phases, status indication via LEDs and LCD, user input via switches and interrupts. This simulation allows us to understand the real-time working of such system without using heavy motors or water flow. Next slide. An embedded system is a microprocessor-based computer system designed for a dedicated function within a large mechanical or electrical system. It combines hardware like sensor, microcontroller with software, firmware or low-level program to operate autonomously. Common examples include microwaves with preset program, pacemaker which monitor and correct heartbeat, car ECU controlling braking and fuel injection, smart washing machine which automatically determines water level, wash time and spin speed. Embedded systems are generally designed to be power efficient, cost effective, and responsive in real time, especially in application that requires automation and precision. Types of embedded system. Functional classification includes real-time system, critical timing like anti-lock braking system, examples airbag, pacemaker, networking system, communicate over LAN internet like smart meter, home automation, mobile systems like portability focused like smartphone, GPS devices, standalone systems, independent operation like our washing machine or like calculators. On the performance-based classification, there are small-scale system built with 8-bit 16 microcontroller, low resource use like toy sensors, medium-scale system, more processing power, possibly multitasking like vending machine, sophisticated system, complex OS-based found in aerospace and robotics like smart traffic system, medical equipments. Our project qualify as a small-scale standalone embedded system using limited memory, no operating system, and single task real time control.
So let's understand the components of embedded systems. And embedded system typically consists of microcontroller, which acts as central processing unit, input-output ports for interacting with external devices like switches, sensor, etc. Power supply, which ensures that we get stable voltage. Communication interfaces such as USART, SPI, I2C for data exchange. Software that we mainly use embedded C or assembly. All these components are integrated onto a PCB and interact seamlessly to carry out predefined tasks. In our washing machine simulator, we connected push buttons for input, LEDs and LCDs for output, and used timers and interrupts for task scheduling, showing how all these elements play a role. Let's understand about PIC microcontroller. The PIC 16F877A microcontroller, developed by Microchip Technology, is highly preferred for learning and prototyping. Key specifications. There are 40 pins with 33 input-output lines divided into port A to port E. US ART and SPI support for serial communication. Timer 0, Timer 1, and Timer 2 for real-time operation. ADC module to read analog values, but it is not used in our case. It operates at 420 megahertz with flash memory for program storage. Its internal EEPROM lets us retain data even after power off, useful for storing wash cycles or mode preferences in real washing machine. We choose this microcontroller because of its flexibility, availability of simulation tools, and wide documentation support. So let's understand the software used. We have used the following tools throughout development. MPLab XID and official ID from Microchip for coding, debugging, and simulation. It helped us structure our embedded C code and debug logic in real time. XC8 compiler, a compiler that translates our embedded C code into hex file executable by PIC microcontroller. PICSimLab, an open source GUI for simulating circuit behavior. We could test logic without connecting hardware physically. PIC Genos, a virtual hardware simulator that mimics real world device behavior like buttons, LCDs, motors, and LEDs. The integration of these tools significantly improve our testing efficiency, especially while simulating various washing codes and timings. Embedded C. Embedded C is a specialized extension of C language with features like direct hardware manipulation via memory mapped registers, efficient memory management critical for low resource environments, support for real life operations through timers interrupts. We organized our code into header files for macros and port configuration, functions for wash, rinse, spin, and other functions, interrupt handlers for external events like start and stop buttons. Using modular design, we ensured reusability, readability, and ease of debugging. This approach also mirrors real world firmware development.
In this slide, we are discuss about peripheral device LED. LED are basic output device, but extremely helpful for indicating current phase, error notification, status tracking. In our simulator, we use port B to connect three LEDs. Use digital signals via code like port B bit RB0 equal to 1 to turn them on off. Timer delay control how long each LED stay on. Reflecting phase duration. LED help us visualizing the machine activity clearly even during the dubbing. In the next slide, we are discuss about peripheral device LCD. The 16 cross 2 LCD was our primary use interface. In display, Startup message, select mode, example quick wash, deep clean. Current cycle, completion notice. Interface was done using data lines connected to microcontroller boot pins. Control lines for read write control. We use custom function like LCD ACMD and LCD data to handle communicate and data. The LCD not only enhance the user experience but also help track the real-time process flow for each operation. For next slide, we are discuss about peripheral device interrupt. Interrupts allow us to break the normal execution flow to handle urgent events. Type we use external interrupt. For user interrupt like start, stop, wire, push button. Internal interrupt for timer flow and very fluidic events. This structure enable non-blocking behavior. For example, pressing the start button trigger an interrupt and begin washing immediately. If stop is pressed, an interrupt driven handle halt the operation. We configure INT0 pin for external input and wrote an ISR for it. For slide 13, we discuss about timers. Timers are essential to stimulate real-time delay and scheduling. For example, timer 1 manage and fix washing duration of 5 seconds. Timer 2 blinking LED every second during spinning. We configure to scale down clock speed. Interrupt flag to trigger event when timer overflow. User pooling and interrupt based approach interchangeably. Without timers, we are forced to use delay loop, which blocking and not efficient. Using a timer given us realistic behavior just like an real appliance. Now turn over to hers.
Now let us walk you through the demo of our washing machine simulator. So this is the PICSimLab. First we select the PICGenius board and choose the PIC16 F877A microcontroller. This is already chosen here. You can see PICSimLab, PICGenius and PIC16 F877A microcontroller is already chosen. After this, we upload the compiled hex file using the load hex option. Once the code is successfully uploaded, a message will appear on the display confirming the initialization. As you have seen that it initialized. To begin operating the washing machine, we press key 5 which power on the system. So like we have pressed the key 5 and it's showing the powering on washing machine. Using the keypad, we can choose desired washing machine program as per the requirement. You can see daily, heavy, delicates, and more different like stain wash, eco cottons, woolens, bed sheets, rinse dry. We can choose any of these. So now turn over to Ayush.
After selecting a program, we long press key 4. This initiates the operating mode, simulating the process of washing clothes. So as you can see, after a few seconds, the system prompts us to choose a water level. The available the levels are displayed as auto, low, medium, high, and max. Once a preferred water level is selected, we again press long key 4. The system will now prompt us to press the start key. Press key 5 to officially start the washing process. Now you will observe the simulated washing process begins, represented through display and peripherals. Now I will turn over to Yash.
To temporarily stop the washing process, press key 6. To resume the press key 5 once again. The motor restart and the process continue automatically after a short delay. To fully stop the machine, we long press 1. This pauses the program until the key is released. Finally, upon completion of the full washing cycle, we have to wait for some time. After some time, a buzzer will sound. A buzzer sound will indicate that the washing program has successfully concluded.
Now let
Turn
us
over to Hertz.
now let us do another simulation. Now we select a different washing program. Now let us try another washing machine program. Now we select a different washing machine program. We choose uh,
For example, we can choose the delegates option. Yes, can you please select the delegate option? So it will now show the different washing modes here. We
now
can see
let's
whites, stain wash, and eco cottons. Choose one.
so for next washing machine program we choose like whites. So now we will select the water level. Let's select low. Now let's press start to start the timer.
So now you can see the now you can see the wash timer has risen up to 1 minute and 28 seconds, and it's now going down. So you can see that different washing modes require different time to function. As you can see in real washing machine, it also takes different time to operate for different modes. So we'll now wait for 1 minute and 13 seconds to see what will.
On the meantime, we can give an interrupt to stop the washing machine, just like just did here. It gives an interrupt to stop the washing machine. But after that, it will further gets to continue. Let's wait for 50 seconds more. In the meantime, I thanks the Emertxe team for for this opportunity. It has been a lot of learning, and I learned a lot of about embedded system, embedded C, and the microboards that we have used. The guidance were very good, and I totally enjoyed this journey of 6 week microcontroller internship at Emertxe.
Yes, same like Harsh. I've also learned about C, but this embedded C was something different. Like it was a different language. Not totally different, but yeah, it was kind of different than C.
Okay, so now the program is completed and it shows remove cloth and the fan is also off and buzzer is buzzing. And now it's again
So
back to the washing machine program screen. So that's our conclusion. Hope you will understand our project and presentation. Thank you.